In this lesson titled Experimental Investigation of Thevenin's Theorem, we plan to do exactly what the title says. Previously, we've examined Thevenin equivalent circuits and Thevenin's theorem from an analytical point of view. You might say with pencil and paper, and we showed how a linear circuit could be replaced by one voltage source and one resistor, that is the Thevenin equivalent, and that the two would be equivalent from the perspective of what was connected to the output terminals of both. As a specific example, for a given load, we would get the same load voltage, load current, load power, regardless of whether that load was connected to the original circuit or to the Thevenin equivalent. Seeing is believing, they say, so let's try it out experimentally. Well, we'll work with this circuit that we see here with the two power supplies and three resistors, and we will also work with the Thevenin equivalent. So first of all, what would be the Thevenin equivalent to the left of terminals A and B? The Thevenin equivalent consists of one voltage source labeled here V sub t, one resistor labeled here R sub t. To carry out the experiment, we have to first of all apply Thevenin's theorem to find, that is, to calculate the values of V sub t and R sub t, and then we can proceed with the experiment. We will build both circuits and generate a table such as we see here, where for a given load we'll measure the load voltage for both the original circuit and also for the Thevenin equivalent circuit, and we'll do that for several different loads. To refresh our memory in terms of getting the Thevenin equivalent, the Thevenin voltage associated with the original circuit is the voltage at the output when the load is an open circuit. We can solve for that value by, for example, superposition, and the result is that the open circuit voltage, therefore the Thevenin voltage, is 1/3 Vs1 plus 2/3 Vs2. We also need the Thevenin resistance, and there are different ways of obtaining this. One way would be to find the open circuit voltage divided by the short circuit current, or since this circuit contains no dependent sources, we may also use the look-back method and find the equivalent resistance when all the independent sources are set to 0. In other words, current sources to open circuits and voltage sources to short circuits. Let's do that here. We'll replace both voltage sources by short circuits. We see all three resistors in parallel, 1 kilo ohm in parallel with 1 kilo ohm in parallel with 1 kilo ohm. Our equivalent is 333 ohms, and that is also the Thevenin resistance. What should we set the Vs1 and Vs2 values to in this experiment? We can choose anything we want since we're setting it up, but for simplicity, I'm going to use a 5-volt voltage source for Vs1, and then I'll select another 5-volt voltage source for Vs2, and since the Thevenin voltage is 1/3 of Vs1 plus 2/3 of Vs2, the value of the Thevenin voltage is therefore 1/3 of 5 plus 2/3 of 5, or 5 volts. So here's our task. Let's build the original circuit with the two voltage sources and three resistors. Then let's build the Thevenin equivalent with one voltage source and one resistor, and proceed. Here's the original circuit built on a protoboard. We have the two power supplies, Vs1 and Vs2. They're off camera here, but they're connected via the red and black leads as you see. We also have the three 1K resistors, and we'll be taking the output voltage where the blue and yellow wires are. As we begin to do our experiment, let's recall that this is the real world with resistors that are plus or minus 5%. One of the power supplies was actually 4.98 volts, the other is 5.01 volts, based on measurements I did a little earlier. So we don't expect 4-digit agreement like on a computer with idealized circuits, but let's see how the experiment goes. Let's see what this circuit delivers to a 1K resistor. So a 1K resistor has been inserted on the protoboard, and the output of the circuit is now brought to that 1K resistor. The 1K resistor is R sub L, the load resistor. Let's set a multimeter, bring it into the picture, put the red lead and the black lead on, and see what we measure. And the measurement is 3.76 volts. Let's record that in our lab book for this experiment. Let's get some more data points. I've replaced the resistor load by 4.7K. Remember, these are plus or minus 5% resistors. And it reads about 4.66 volts. We'll record that also. Now for a little variety, let's try a 470 ohm resistor. The multimeter has automatically switched precision scales. It now reads 2.936 volts. And for our last resistor load, we're going to use a 47 ohm resistor. And that gives us a value of 0.611 volts. Now let's try the Thevenin equivalent. We're going to have a power supply corresponding to V sub T for this particular circuit. As we've discussed, it's 5 volts. We have a 330 ohm for our Thevenin. And again, we're going to attach various loads to the output, and we're going to compare that to the original circuit. For the 4.7K load, we read 4.67 volts. With a 1K resistor load attached to the Thevenin equivalent circuit, we read 3.77 volts. And what do we get with the 470 ohm resistor? 2.952 volts. And finally, for the 47 ohm resistor, I measure 0.617 volts. I wonder what would happen if I attached a nonlinear load, an LED. Well, the diode lights up. Let's measure the voltage across it. The voltage across the diode is equal to 1.868 volts. Now, if I apply that diode to the original circuit, will I get the same voltage, or are all bets off because it's nonlinear? Here's the original 2-power supply circuit. Let's put in the LED. And again, it lights up. Let's measure the voltage across it. And the voltage is 1.869 volts. Here, by the way, is the data as recorded in the lab book. Without getting too much into detail, I'd like to point out for all the loads we used, the voltage across the load for the original circuit and for the Thevenin equivalent are within 1% of each other, certainly within experimental error of measurement, particularly when we consider that the resistors alone are plus or minus 5% components. As we look back on the results of these measurements with different loads, I think we can gain some insight by considering a graphical or a pictorial view. That original circuit that we built had a particular open circuit voltage, particular short circuit current, and it was a linear circuit, that it has linear current voltage relationships. Well, 2 points make a line. The slope of that red line is related to R Thevenin, and no matter what is connected to the original circuit, the resulting current and voltage that result have to fall along the red line that we see here. Now, the Thevenin equivalent circuit that we built has the same open circuit voltage, the same short circuit current, so the red line also indicates the current voltage characteristics of the Thevenin equivalent circuit. Well, the original circuit's not the only thing bringing some requirements to the table. Whatever is being connected to those output terminals also has constraints on current and voltage. For example, say we're connecting a 1 kilo ohm resistor. The blue line shows the IV constraints of a 1 kilo ohm resistor. Now, the two sides of the table can come into agreement when both of their conditions are satisfied. In other words, when the red line and the blue line intersect. And that intersection, based on a mathematical solution using Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law, yields an intersection at 3.75 volts. Now, that calculation assumes all resistors have exactly their face value, and so do the power supplies. In our actual measurements on the circuits, we found load voltages of 3.76 volts for one circuit and 3.77 volts for the other, both within 1% of the ideal circuit calculations and well within the experimental error based on tolerances associated with the components. And now with that perspective, let's return to what we found with the diode. There is an exponential relationship between the diode's current and voltage, decidedly nonlinear. However, the nonlinear diode and the linear circuit can again come into agreement on current and voltage, and that will be at the intersection point. For both the original circuit that we built and the Thevenin equivalent circuit that we built, when we assigned the LED to the output, we found a 1.87 volt voltage drop across the LED. As far as the LED was concerned, they were equivalent circuits, resulting in the same current and voltage for the LED and the same light output. So we may note that although a Thevenin equivalent can only be applied to a linear circuit, once you've got that Thevenin equivalent, you can use it for both linear and nonlinear loads. Let's summarize our experiment. We built two circuits, one with two voltage sources and three resistors, and the other circuit was the Thevenin equivalent of the first, consisting of one voltage source and one resistor, the values of which were obtained by applying Thevenin's theorem to the original circuit. Looking at a variety of loads attached to the outputs, both circuits provided the same result. So from the load's perspective, they were equivalent. Thus, we've seen experimental demonstration of the validity of Thevenin's theorem in electrical circuits and systems, and we see the applicability in that a determination of a load voltage is much simplified if we know the Thevenin equivalent of the circuit it's being applied to.